So this is 10.57, and we're given some chemical equation pieces, so that means we're going to use stoichiometry along with our gas laws pieces in these problems. Metabolic oxidation of glucose in our bodies produces CO2, which is expelled from our lungs as a gas. Here's the balanced equation. Then it says calculate the volume of dry CO2 produced at body temperature, 37 degrees Celsius and 0.970 atmosphere, when 24.5 grams of glucose is consumed in the reaction. So step number one in the stoichiometry problem, remember, is always to write the balanced chemical equation. Step number two, convert to moles, and so we're given 24.5 grams of glucose, C6H12O6. Put a multiply sign, put a line. Put grams here, put moles of the C6H12O6 in a position where it's going to be your new set of units. And in 1 mole, when you add that up, I believe it adds up to 180 grams. Let me just check that for sure. Yep, 180.1 grams. And then that's step number 2. Step number 3, then, we want to go from glucose, which is C6H12O6, to the asked for units. And the thing that we want to know is CO2. So you put CO2 up here as your new desired units. And in the balanced chemical equation, there's a 6 in front of the CO2 for every 1 mole of glucose, which is right here, 6-to-1 ratio. So 24.5 divided by 180 times 6 gives us a 0.816 moles of CO2 that's going to be produced. Now, they don't ask for the moles of CO2, and so this is step number 4 of stoichiometry, convert to the asked for units, and in this case they want to know a volume, and for us to find a volume we are going to use PV equals nRT since it's a gas. Solving for volume, we divide both sides by P, the P's go away, and our volume is equal to nRT divided by P. So our moles are 0.816 moles of CO2 times R. Now the R depends on the pressure units we're given, and we're given atmospheres right here, so we're going to use 0.08206 liters times atmospheres per mole times Kelvin. And then our temperature, it says, is 37 Celsius. So be careful, make sure that you add 273 to that. So it's actually 310 Kelvin. And then divide that by the pressure. And the pressure, it tells us in the problem, is 0.970 atmospheres. So put your units in and then check to make sure that they cancel. The atmospheres with the atmospheres, the kelvins with the kelvins, the moles with the moles, and then you're left with liters. And so your volume is going to end up being 21.4 liters for letter A. All right, in letter B, it says calculate the volume of oxygen you would need at 1 atmosphere and 298 K to completely oxidize 50 grams of glucose. So now this time they give us the balanced chemical equation right here. Then they give us the mass of glucose once again, so we can convert that to moles. But this time the ratio, the step 3 that we did right here, that's going to be between glucose and oxygen this time. And then it asks for volume, so we'll use PV equals nRT at the end. So let's just outline those steps again in case you want to write them down. Step number 1, remember, is to balance the equation. Step number 2, when in doubt, convert to moles. Step number 3 is to use the mole-to-mole ratio from the balanced chemical equation. And then step number 4, convert to whatever asked for units they have. So let's walk through them step by step. First one, balanced chemical equation done for us. Step number 2, convert to moles. So we're given 50 grams of glucose. So way over here on this side, I'll put the 50 grams of C6H12O6. Multiply sign, put a line. Grams of glucose in a position where it's going to cancel. Moles of glucose as my new set of units. And for every 1 mole, there are 180 grams. Remember, I added that up on the periodic table up here. Third step, mole-to-mole ratio. And so here we're going to use C6H12O6 in a position where it's going to cancel, and we're going to put oxygen as our new set of units because that's what it asks for. So the asked for units go on the top. And for every 6 oxygens, there's 1 glucose. I get that right here, 6-to-1 ratio. Punch the buttons into your calculator there for this one, and we end up with 1.67 moles of oxygen. Now, if it asked for just moles of oxygen that are produced, we'd be done. But it doesn't. It asks for specific units. It asks for liters or for volume right here. And so we're going to have to use PV equals nRT again, and V is equal to NERT divided by P right here, nRT divided by P, and our moles are 1.67 moles. The R, careful what units you're using for pressure, and it's atmospheres, so that's going to be 0.08206 liters times atmospheres per mole times Kelvin. And then our temperature, it says, is 298. And then we're going to divide that by the pressure, which is 1 atmosphere. All right, atmospheres cancel with atmospheres, our kelvins with our kelvins, our moles with our moles, and we're left with liters for our answer. And so when you plunge those into your calculator, you should end up with 40.7 liters of oxygen.